Okay, let's unpack this. Imagine finding a message in a bottle, but the bottle is a rock, and it's from Mars.
Hey, that's a great way to put it.
Right. We're stepping back billions of years today, thinking about a Mars that might have been w- alive.
A very different picture than the desert we see now.
Exactly. And we have this incredible robotic explorer, NASA's Perseverance rover, digging through ancient riverbeds, sending back flues.
Clues that could genuinely rewrite the books on life in the universe.
So that's our mission for this deep dive. What did Perseverance actually find? Why are people calling it the most compelling potential biosignature detection to date?
And what does it all mean for that huge question? Are we alone?
We'll be digging into the latest reports, the science papers, trying to get you the core insights.
And it's fascinating stuff because, it's not just about finding weird rocks. This touches on how life itself might even start, biogenesis.
Right, the origin of life.
If these findings really hold up, it suggests life might pop up more easily than we thought in different kinds of places.
Kind of challenges that rare earth idea that life like ours is incredibly unique.
Precisely. It potentially opens up, well, a universe of possibilities.
Okay, so the hero of this story is Perseverance. This amazing rover landed back in 2021.
A complex piece of engineering.
Totally. And its job, its main goal, was crystal clear. Look for signs of ancient microbes, past life.
And it's been busy. 4 years exploring the Jezero crater.
Which wasn't just picked at random, was it? They chose Jezero specifically because all the evidence points to it once being a lake.
Fed by a river billions of years ago, a watery environment.
Just the kind of place you'd expect life, if it ever existed there, to maybe get started. So different from Mars today.
That dry, cold desert.
Yeah. But here's where it gets really interesting. Last year, Perseverance was down in this canyon, carved out by that old river, an area they call the Bright Angel Formation.
Mm-hmm.
And it found these mudstones, ancient rocks, right? About 3.5 billion years old.
Very old, even by geological standards.
And they're covered in these weird little markings. Scientists nicknamed them leopard spots and poppy seeds.
Catchy names.
Definitely memorable. And these tiny features, these spots and seeds, are what's causing all the buzz.
And this is where, our understanding of Earth geology helps. These aren't just random dots.
Okay.
The scientists think these features, especially these tiny iron-rich balls inside the leopard spots, contain minerals. Minerals made by specific chemical reactions.
Right, specific reactions.
And those reactions and the minerals left behind. Well, that's the key. On Earth, in similar ancient environments, making those minerals often involves microbes.
So there's a direct parallel to life processes here.
There's a very strong parallel. It's a signature we recognize.
Which brings us to this term the scientists are using, potential biosignatures.
Right. It's careful language.
It means basically, this looks really promising, like it could be life, but we need to be absolutely sure.
Right. Exactly. It's a strong lead, something that warrants a lot more investigation. Science demanding rigor.
So they're weighing two main ideas, two hypotheses for how these features formed.
Mm-hmm.
One, they were made by chemical reactions linked to ancient Martian microbes. That's the biological origin.
The exciting one.
Definitely. Or two, they were made by just plain old geology, natural processes that happen to look a bit like biology, the non-biological origin.
And figuring out which one is correct is the multi-billion-dollar question, really.
You can really feel the excitement, maybe a bit of caution, too, from the scientists involved. Like Professor Sanjeev Gupta. He's at Imperial College London, co-authored this study.
Yes, I saw his comments.
He said something like, "We've not had something like this before, so I think that's the big deal." He stressed they aren't saying they've found life, but that it gives us something to chase.
A very important distinction. Evidence, not proof. Yet.
And Dr. Nicola Fox from NASA Science used this great analogy, like finding a leftover fossil. Maybe it was a leftover meal. Maybe that meal's been excreted.
Huh. A vivid picture.
Right. And then Dr. Joel Hirowitz, lead author on the paper from
Right.
Stony Brook University, he got into the nitty-gritty.
Okay.
He explained they think they found evidence for chemical reactions in the mud at the bottom of the ancient lake. Reactions between the mud and organic matter.
Organic matter. Okay. That's a key ingredient.
And these reacted to form new minerals.
Mm-hmm.
And then he said the line that really stood out. This feels like the most compelling potential biosignature detection that we've had to date.
That's a strong statement from a lead author.
It really is.
And this raises an important question. Why is the non-biological pathway maybe less likely here? What makes this lean towards biology?
Good question. What's the evidence against just geology doing this?
Well, Dr. Hurwitz's team looked into that really deeply. They explored how you could get these minerals without life.
Okay.
And while you can't totally rule it out, those non-biological ways usually need high temperatures, heat.
Oh.
But crucially, he pointed out, the rocks don't look like they've been heated. There's no sign of that kind of thermal alteration.
So the rocks themselves argue against the high heat geological process.
It seems so. He said they found some difficulties for the non-biological pathways, which, given the Earth comparison, where microbes often do this, well, it tilts the balance.
That does make the biological explanation sound more plausible, doesn't it? But how does that scientific debate actually work? Are they, like, trying to disprove the life angle?
Oh, absolutely. That's fundamental to good science. You have to try and break your own hypothesis.
Right, falsification.
Exactly. So while some scientists are building the case for biology, others are actively hunting for that geological gotcha, some non-biological process that perfectly explains everything without needing microbes.
A scientific tug of war.
It really is. And it can get quite passionate because, finding life on Mars,
Yeah.
the stakes couldn't be higher.
So for you listening, what this boils down to is we've got this really compelling evidence, features on Mars, that if you found them here on Earth, you'd pretty much immediately say microbes did this.
Mm-hmm. Strong indicators.
But science, especially for a claim this big, needs absolute certainty. Proof positive.
Yeah.
So a huge clue, maybe the best one yet, but not quite the final word.
Not yet.
And to really get why this is so significant, we need to remember what Mars used to be like billions of years ago.
Yeah, rewind the clock.
Today, it's that cold, dry, radiated desert, thin atmosphere, pretty harsh.
Very harsh for life as we know it.
But the evidence is just overwhelming that ancient Mars was different. It had a thick atmosphere, probably a magnetic field,
Protection from radiation.
and water. Lots of liquid water. Rivers, lakes, like the one that filled Jezero Crater where Perseverance is.
A warmer, wetter, more chemically active Mars. Potentially a habitable Mars.
Exactly. With energy sources, chemical building blocks, the stuff life seems to need.
In that context, the fact that Mars could have supported life back then is critical.
It's not just finding weird rocks anywhere.
No, it's finding weird rocks in a place that was, theoretically, an ideal spot for life to get going. Jezero Crater was chosen for that exact reason.
Because it was an ancient lake bed with a river delta.
Precisely. So finding potential biosignatures there fits the picture perfectly. It makes the biological explanation even more plausible because the environment was right.
Okay, so Perseverance finds these rocks. How does it actually analyze them way out there on Mars?
It's got this incredible suite of instruments on board, basically a mini laboratory on wheels.
Lasers and spectrometers and cameras.
All sorts of advanced tech. It performs what they call in situ analysis, studying the rocks right there, looking at minerals, textures, chemistry.
And then all that data gets beamed back here across millions of miles.
Yep, sent back to Earth for scientists everywhere to pore over, debate, analyze further.
But Percy, as they sometimes call it, isn't just looking. It's also collecting, right? Taking samples.
Yes, and this is absolutely crucial. It's been drilling core samples from interesting rocks, including from this Bright Angel Formation.
Like little pieces of chalk.
About that size, yeah. And they're sealed in these super clean tubes, these canisters.
Keep them pristine.
Exactly. And then the rover has been dropping these sealed samples at specific locations on the surface, creating a depot.
Leaving them there for pickup later.
That's the plan. Waiting for a future mission designed to bring them back home to Earth.
Which brings us to the next, maybe the hardest step.
Indeed. What's fascinating here is the sheer complexity and importance of this next phase, actually getting these precious samples into labs back here.
Because as good as Perseverance's instruments are,
They can't match the power and range of instruments we have in labs on Earth. For that definitive, yes, this was life, answer, we need the rocks here.
I remember hearing someone say they're probably the most expensive rocks ever collected, even before we try to bring them back.
Huh, probably true. It speaks to the effort and the potential payoff, but, and this is a big but, that sample return mission is looking shaky.
Oh, so?
The plan, a joint effort between NASA and the European Space Agency, ESA, well, its future looks highly uncertain.
Why? What's the problem?
It comes down to funding. There are reports of huge cuts being proposed for NASA's science budget in the U.S.
Budget politics.
Seems so. And the Mars sample return mission is apparently one of those potentially on the chopping block, facing cancellations according to some budget proposals.
Wow. After all this work finding these potentially groundbreaking samples.
It highlights the challenges, doesn't it? Incredible science, but massive costs and, well, political realities.
And it's not just NASA and ESA in the game, is it?
No, space exploration is increasingly international. China is also working on its own Mars sample return mission.
Tianwen 3, I think?
That's the one. Could launch as early as 2028, potentially. So there's an international dimension, maybe even a bit of a race.
You can just imagine the scientists.
Yeah.
They must be desperate to get their hands on these samples.
Oh, absolutely. Professor Gupta said it plainly. We need to see these samples back on Earth. He emphasized that for real confidence, most scientists want to examine them here. He called them one of our high-priority samples to return.
The ultimate lab test.
It really is. If we connect this to the bigger picture for you, the listener, analyzing these samples on Earth is the only way we'll know for sure about past life on Mars.
All the clues Perseverance has gathered, the leopard spots, the mineralogy, it all points tantalizingly.
But that final, undeniable proof, that smoking gun, it relies entirely on getting those rocks into our advanced labs here.
Which really underlines the stakes and why scientists globally are hoping these sample return missions somehow, go ahead.
Absolutely. The potential discovery is just too profound.
So recapping our deep dive today, we look at truly captivating evidence from Mars, features in ancient rocks.
About 3.5 billion years old.
That here on Earth would scream life. These leopard spots and poppy seeds in Jezero Crater's Bright Angel Formation.
Found by the Perseverance rover.
We've explored why the specific minerals and chemical reactions have scientists so excited, making a strong case for biology.
While still acknowledging the need for absolute proof. Scientific rigor.
And we've looked at that crucial next step, getting the samples back to Earth. A vital step, but one facing significant hurdles.
Huge hurdles, which leads to a final thought, maybe.
Go for it.
This raises an important question for you, the listener. If, and it's still an if, but if these rocks do confirm ancient Martian life, what does that actually change for you? For us?
Our place in the universe.
Does it make life seem less special or just more common, more likely to arise elsewhere? And thinking about those budget challenges, what responsibility do we have as a species to chase these big answers, even when it's incredibly difficult and expensive?
Knowing the discoveries could change everything.
Profound implications, something to ponder.
Definitely something to ponder. It's a journey that just keeps pushing our understanding, expanding our cosmic view. Keep looking up, keep asking those questions.
And stay curious.